In probability, independent means that the probabilities do not change. The probability of something happens regardless of anything else that happens. Conditional probability is the opposite. Conditional probability means that the probabilities do change depending on something else happening. So, a bag of 3 red and 2 blue marbles are put in a bag, and that's my weak artistic impression of a bag, but as you can see there are 3 red, 2 blue. Draw a probability tree showing the outcome of the 2 draws. Okay, so what we would do then is we would start at the beginning. So this is before we do anything, before we draw any marbles out. What's the probability that we draw a blue marble, and what's the probability that we draw a red marble? Okay, well, how many blue marbles are there? There's 2 blue marbles and 5 marbles in total. How many red marbles are there? Well, there's 3 red out of 5 in total. Okay, now once we've chosen, say we chose a blue marble, now there's 2 possible outcomes of our second choice. Either we can choose blue again or red for the second time. What's the probability now of choosing blue? Well, there's only 1 blue left. You already took it, and there are only 4 marbles left. If we took a blue the first time, how many red marbles are left? Well, there are 3 red marbles left and 4 marbles in total left in this bag. Okay, let's do it again for this one. So this time we chose red the first time. Now what's our probability that we choose blue? Well, if we chose red the first time, there's still 2 blue marbles, but there's only 4 left. And if we chose red the first time, now there are 2 red marbles and 4 marbles in total. Okay, what is the probability that both marbles are red? Well, the rule is we multiply down the branches and add between branches. You'll see what I mean in a second. Okay, so red, that one and that one. So we multiply the probabilities down the branches. So the probability of getting red is going to be equal to 3/5, which is the probability that we got red the first time, times 2/4. So the answer is going to be 6/20, which is the same as 3/10. That's our probability. If we take the marbles out and don't put them back it's conditional. Just as a side note, what would be the probability of getting 2 blue marbles? Okay. Probability of blue, then blue, is going to be the probability that the first one was blue, which was 2/5, times the probability that once the first one was blue, the second one was blue again, that's going to be 1/4. And when we multiply those together, we get 2/20, which is 1/10. Okay, what's the probability of getting at least getting 1 red and 1 blue? We don't care when they came out. Okay, which of these 4 outcomes meet that criteria? Well, this is red, so obviously that doesn't count. This is red-blue, so that counts. So it's going to be 3/5 times 2/4. And this one is blue then red, and this one is blue, so that doesn't count. So blue-red is going to be 2/5 times 3/4. And we will jump on the calculator, good old trusty Casio calculator, and work out our answer. So our answer is going to be 3/5 times 2/4 plus 2/5 times 3/4, and the answer is 3/5. So about, well, not about, but 60%. And that's basic conditional probability. Now we get a fairly common exam question. In a school, 70% of the students wear a uniform. Of those who wear a uniform, 80% arrive on time. Of those who don't wear a uniform, they only arrive 50% of the time. Okay, so let's do a probability tree. So here is a student chosen at random. So this is uniform, and this is no uniform. So 70% of students wear a uniform, and I guess that means 30% do not wear a uniform. Alright, fair enough. Of those who wear a uniform, so that's the 70%, 80% arrive on time. So this is on time. And 80% of those. So I guess that means late 20%. So they're either early or they're late. It has to add up to 100. Okay. Of those who don't wear a uniform, on time, those who don't wear a uniform, 50% arrive on time. So I'm just going to go OT, 50%, and late 50%. Okay. Now we want to multiply down the branches and do that as a decimal. You don't have to do it, but I'm just going to complete it and do fill in all of these gaps. So 70% is 0.7 times 0.8, which is 0.56. So in other words, if you chose a student at random before you knew anything about them, whether they had a uniform or not, there would be a 56% chance that they did wear a uniform and they were on time. Okay, wear a uniform and are late. So 0.7 times 0.2 is 0.14. 0.14. And now down this branch, down there and then up there. So 0.3 times 0.5 is 0.15. And it's going to be exactly the same for that because it's the same probabilities. Okay. What is the probability that a student chosen at random both wears a uniform and is on time? Okay, so we already answered this question. It's 0.56. 0.56, which is the same as 56%. A student is chosen at random and is on time. What is the probability that they were wearing a uniform? Okay. So now we're looking at comparatives, aren't we? So 0.15 of the school, no uniform but on time, and 0.56 of the school, uniform and on time. So what is the probability that they were wearing a uniform? It's going to be this divided by all of the students that were wearing a uniform. So it's going to be 0.56 divided by 0.15 plus 0.56, because this is the proportion of all the school there, so we can get away with doing that. And I've got no idea what that is off the top of my head, so 0.56 divided by brackets 0.15 plus 0.56 equals 70, we'll say 78.9%. F. And that's how that's done. For this one, we're told that a game involves drawing 2 cards from a hat, so presumably you can't see what you're drawing. There are 5 cards, 3 with stars, 2 with hearts. The cards are drawn without replacement, so in other words, you take it out, you have a look at it, make note of it, and put it to the side. You don't put it back into the hat. Okay, draw a probability tree showing all possible outcomes from these 2 cards. It's pretty similar to the marbles example by the looks of it. Okay, so here's our hat. So it's like a Abraham Lincoln hat. And there are 5 cards. There are 3 with stars and 2 with hearts. 1 and 2. It's a little heart. So there are 5 cards in total. Okay, first guess. You put your hand in, and your probability of drawing a star. There are 3 stars and there are 5 cards. Your probability of drawing a heart is 2 out of 5. There are 2 hearts cards. There's 5 cards in general. The next one, you can draw a star and a heart and a star and a heart, kind of wobbly looking heart. Now what are the chances of getting a star? Well, one of the stars is gone, so now it's only 2 out of 4, and both of the hearts are there, but there's only 4 cards left. Okay, say you drew a heart the first time. How many stars are there? All 3 stars are there, and there are 4 cards left. How many hearts would be left? Well, only 1 of the 4 would be a heart. So, what is the probability that at least 1 card is a heart? Well, it's going to be everything except that one where you get star, isn't it? So let's work out the probability of star, and that's going to be 3/5 times 2/4, which is going to be 6/20 of getting star. Now each of these ones, that has a heart, that has a heart, and that has a heart. So the probability of at least 1 heart is going to be equal to 1 minus 6/20, because they all have to add up to 1. So 20/20 minus 6/20, 20/20 is 1, is 14/20. And that's our answer. If we wanted to do it as a decimal fraction, it's going to be that 0.7.